Okay, so we've looked at having initial velocities in different directions and how that changes which components exist. But we want to see how this relates to the kinematics equations and how we can use this knowledge to customize the kinematics equations for whatever particular projectile motion problem we're given. Now, each of the different possibilities for something to be launched outward, you could launch it straight up, you could launch it horizontally, you could launch it at an upward angle or a downward angle. Each of those is going to get a different set of kinematics equations that are going to be used in solving those particular problems. But rather than trying to memorize all those different possibilities, it's much better to take the generalized equations that you already know and apply them to whatever problem by customizing them so that they fit the problem based on what's given in the problem. So here I have the first two kinematics equations and I've duplicated them because as we talked about, we're going to break the motion of the projectile into an x motion and a y motion. Now, we know just from our own experience that when I launch something up at an angle, it's going to follow some kind of curved path. But this complicated curved path consists of two motions simultaneously. There is an up-down motion as it goes up and then comes back down, and then there's a left-to-right motion. And so as it's going along its path, it's going up and down at the same time that it's going left and right. Rather than trying to analyze those two things at the same time, we're going to break them up into the x motion and the y motion. And so that means we have kinematics equations that are customized for each possible motion. I have an x velocity and an x position. I have a y velocity and a y position. This is the first kinematics equation. V is equal to v naught plus at, but I've just added a little subscript x to let me know that that's talking about the motion along the x-axis. And here I've taken the same equation and added a little subscript y to every term where it's relevant, and that lets me know that that's talking about the y component of the velocity. Same thing for position. This is the x position. Everything is in terms of the x components, and here's the y position. Everything is in terms of the y components. So let's say we're looking at a problem, and the problem says that a projectile is launched horizontally off of a cliff that's 100 meters high. And so what we're going to look at today is not how to actually solve anything about this problem, but just how to set it up. How do we set up a problem, any problem, where something is launched out horizontally? And so what we know is we have our equations that we saw on the previous slide, the two for the velocity and the two for position. And what we want to do is we want to pick our coordinate system, and I like to pick it in the usual way. I like to put the origin of my coordinate system where the thing is launched from, because that will make x naught and y naught 0. And then I just customize them by plugging in the things that I know. So what are the things that I know? We've already talked about, we know that the x component of the acceleration is 0. So everywhere I've got an a sub x, I plug in 0. And again, if a problem said there was a horizontal wind creating a negative 6.0 meters per second squared acceleration in the x direction, you'd plug in negative 6 there. You just plug in what you're given in the problem. But for most problems, the x component of acceleration is going to be 0. Now, I know that v naught x is v naught, but v naught y is 0. Because my v naught is horizontal, there is no y component to that vector at all. And so anywhere that I have a v naught y, I can cancel that term. So that term goes to 0. That term goes to 0. That whole term goes to 0, v naught yt, because anything multiplied by 0 gives you 0. And of course, we know that the initial position is 0. Those terms go to 0. Why? Because that's where I put the origin of my coordinate system. I made them 0 by putting my coordinate system there. And then the last thing that we know that we can plug in is we know that a sub y is equal to minus g. So I can plug in minus g everywhere I have a sub y. So really all I'm doing is I'm looking at what's given in the problem and I'm figuring out which of those components for v, for a, for x, and for y, which of those components are 0, and I'm just throwing those away. And then I take little g and plug it into a sub y. And that results in equations with a bunch of terms going to 0 and being eliminated, and what's left over is this. We get Vx is equal to V naught x, and of course we know that V naught x is just the initial velocity V naught. And in a problem, again, it's going to say a projectile is launched 50 meters per second horizontally, and so V naught would be 50 meters per second, and that's constant. Now our Vy works out to be minus g times t. Our x position is V naught x times t. Now again, what are these? What is Vy here? That is the y component of velocity at any time t. And so at t equals to 3 seconds, I plug in 3 here, I multiply it by negative g, and that tells me what the y component of the velocity is at that time. Up above, we see that Vx is constant, so no matter what time you're looking at, it has the same velocity in the x direction, the velocity that you started with. Again, we're assuming there's no air resistance here, nothing to slow it down or speed it up. Now our x is V naught xt. What's V naught x? That's the V naught again. And our y is minus 1/2 gt squared. And so again, this x, this t, they're the x and y positions of the projectile at any time t. I plug in 16 seconds, I know what my x position and my y position are at 16 seconds. It's that simple. Now here's another example, but this time we're having something launched vertically upwards. And so different things go to 0 than in the previous case. So some of the things are the same. We know that ax is going to go to 0, so all of those terms go away. X naught and y naught go to 0, but previously the v naught y went to 0 and the v naught x was held, but here it's the reverse. The v naught y is still there, but everywhere there's a v naught x, that term goes to 0. That term goes to 0. And so, and of course we know that ay is minus g. That ay is going to be minus g. And so again, we can customize these equations just by plugging in what's 0 based on looking at the components of each of these things. The components of the acceleration, which is only negative g. The components of velocity, which is only positive v naught in the y direction. And then we have the position components, which for x naught and y naught are at the origin. And when you get rid of all the terms that are 0, the first thing that you can see is that all the x equations go away completely. And that makes sense because what we have is this is going to be launched straight up, it's going to go up, it's going to come back down. It might miss the edge of the cliff and fall to the ground below, but basically it's not going to move left and right at all. So there is no x motion to consider, it's all y. And we can see that the equations that we end up with are different from the equations that we got from the horizontal case that we did previously. But this is not a set of equations to memorize. Don't memorize, oh, if it's shot up, use these equations. Learn how to customize by plugging in what's 0. That's way better because you won't mix it up with the other cases. You won't forget it the day after the test. If you understand the process, then you'll remember this for a very long time and it'll be easy for you to work these kinds of problems. So here's an example. We have something a little different. Instead of it being shot at an upward angle, which you often see in these kinds of problems, just for fun, we've got the example with it shot at a downward angle. And so you can see it's going to be have an x component and it's going to have a y component of the initial velocity, but the y component is in the negative direction. My positive y is pointing up because that's how I define my coordinate system. And so again, we have our full set of kinematics equations. Now, the only thing that's really different when it's shot at an angle, upward or downward, is that you have both the x and y components of the initial velocity. None of them go to 0. And from trig, we can write them down in terms of the sine and the cosine. V naught x is v naught cosine of theta, v naught y is v sine of theta, where theta is, of course, the angle that the initial velocity vector makes with the x-axis. Now, again, just to be sure we remember, the key thing with the downward angle is that that y component is negative. And so we want to make sure we remember that when we apply it to a problem. So once we realize that, we can go to the process of customization again. We know everywhere there's an AX is 0, so we can just cancel those real quick. My X naught and my Y naught go away. My V naught X and my V naught Y, they all stay, but my A sub Y is again minus G. I can plug in minus G there as well. And so now I just throw away everything at 0 and write down what's left, and I get equations that are customized for this problem. But we have to keep in mind we know what those components are, V naught X and V naught Y, and we also know that that Y component is negative, and so we want to remember that. So keeping that in mind, we see what we end up with the customized kinematics equations for something shot at a downward angle. And the key thing here that we notice is that that Y component of the initial velocity is negative, and everything else is pretty straightforward. Now, of course, we can also look at how it works for an upward angle. Everything else is the same except for that V naught Y is now pointing in the positive direction. And so I can do my customization. That term goes to 0. The AX goes to 0. Why does the AX go to 0? Does anyone remember? Why does the AX go to 0? Because which way do things fall? They fall down. Gravity pulls down. Gravity is what's causing the acceleration, and it points down. So there's no gravity making something accelerate left or right. That means the AX is 0. So I can cancel them out. We know X naught and Y naught are 0 because that's where I put my coordinate system. And we know that AY is minus G. Plugging those in, I get my customized kinematics equations, which look something like this. This gives us Vx is constant. It's equal to the initial velocity in the x direction. Vy is not constant. It depends on time. So if you ask me what is the y component of the velocity at 3 seconds, I plug in 3 seconds here, and that'll give me my answer. This is the position in the x along the x-axis, so this is how far it travels horizontally at any time t. This equation is the y equation, and this tells you how high it is or how low it is, again, at any time t that I want to plug in. And so these 4 equations, they will be used to solve any projectile motion problem that can be thrown at you. So let's take a minute and see how we can use these equations to analyze some features about the motion. So we have the 2 position equations. Now this is for the case of something launched at an upward angle. So I've got a V naught at some upward angle, and I've got my y-axis like that and my x-axis like that. And there's some angle theta here. And of course, we can take our V naught and break it down into x and y components. And when we do that, we end up with kinematics equations for position labeled here as 1 and 2. So this is the x position as a function of time. This is the y position as a function of time. Now, the thing that we can notice is that x varies linearly with time. T goes to the power of 1. But the y position varies quadratically with time. It has to the power of 2. The t variable is taken to the power of 2. It is essentially going to be a quadratic equation here for the y position and a linear equation for the x position. So the x and y positions both depend on the time, the variable t, and so that means that together they form what's called a set of parametric equations. So I have my x position as a function of time and my y position as a function of time. And so I can say, okay, let's look at t equals to 0, t equals to 1, t equals to 2. And as I increase t, these guys are both changing. And so they depend on the parameter t. That's why they're called a parametric equation. And so you can actually, so for every value of t, you could plot not on x versus t or y versus t, you could plot on a regular y versus x coordinate system. So I plug in t equal to 0 and I get a point. I plug in t equal to 1, I get a position for the x, I get a position for the y, at 1 second. And so this would be the point for 1 second, and this might be the point for 2 seconds, and the point for 3 seconds, and so on. So every time I get a point for both x and y that I can plot on a regular xy coordinate system. And so that is why it's called a set of parametric equations, because you have two related equations that depend on the same parameter t. So we want to see, how does the y and the x relate to each other? And so the way we can look that up is we can eliminate the variable t. Now, up here in the upper right in this box, I have my two position equations. What I want to do is I want to solve the x equation for t and then plug it in here, and then I have eliminated t as a variable. T will no longer appear in the equation, and I can analyze what the motion looks like. And so if I take this top equation here and I solve for t, I'm just going to divide both sides by v naught x, and I get that t is equal to x divided by v naught x, and then I can plug that into the y equation. So this stuff in the parentheses here, this whole thing here, that's just t. This guy here, that's t. And of course t squared. And so I've just plugged in x over v naught x into these times in the y equation. And when I simplify everything, I get this for my y. And now I have a y value written not as a function of time, but as a function of x. And look at that form. It's y is equal to v naught y over v naught x. That's a constant. And also this guy here is also a constant. So both of those guys are constants. So y is equal to some constant times x minus some constant times x squared. And we can also note that the constant in front of the x squared term is negative. And so I've got some constant 1, some constant 2. I can rewrite this equation to simplify it. And I end up with y equal to some negative constant x squared plus some positive constant x. And that is the form of a parabola. Y is equal to x squared. And so if I plot, y as a function of x, what I end up with is an inverted parabola. Inverted because of that minus sign there. And so this tells us that the motion of a projectile is going to follow the shape of a parabolic path. And so we talked about how if I throw something up, it's going to follow some complicated curved path. Now we know exactly mathematically what that path is. It's just a parabola, and that is pretty darned cool. Now I want to look at a few other aspects of this motion. And so I have the x and y coordinate systems here, and I've plotted the path of a projectile, which we now know is going to be a parabola. And so I've got these pink vectors here, which are the velocity at any time. And so I picked a few different times and I've drawn in the velocity vectors. Now we know that the velocity vector of an object moving on a curved path is always tangent to that path. That's one of the things that we saw in one of the earlier kinematics videos. So as this projectile moves along this parabolic path, if I pick any point on it, the velocity vector is going to be tangent to that parabola at that point. Now, one of the things that we know, if we consider the velocity vectors, we have the formulas for the velocity as a function of time. Now, the x component of the velocity is constant. There's no acceleration in the x direction, so the x velocity doesn't change. And so if we look at the x component of the velocity at each of these points, it's the same length, or at least if I had drawn it perfectly, they would all be the same length. So this guy is not changing. But the y component, look here, I've got a bigger y component, my y component is shrinking, and then at the tip top, the y component goes to 0, because the y component of velocity has to stop in order for it to change direction along the y-axis and start coming back down. And on this side, on the right side of the parabola, you can see the y component is turned negative, and it gets bigger as it falls because the object is speeding up. And at every point, if I know what time that happens, I just plug in the time here, and that tells me what the y component of that velocity is at that time, positive or negative, depending on which side of the parabola it's on. And of course, again, the Vx, it just stays constant. It doesn't change.